Hi everyone. We are up to lecture 14 in the Total Notes PDF. Today I'm going to be continuing with the idea of testing for prime numbers, where we left off yesterday. We were chasing down Fermat's little theorem and trying to see when we could detect prime numbers when we ran into the problem of pseudoprimes, and in particular, the Carmichael numbers, which are pseudoprimes that will beat every possible test that way. Today, we're going to take another stab at building up a primality test, and this one picks up with the Fermat equation, but we're going to start to think about square roots modulo n, and the formal name for the test we're talking about is the Miller-Rabin primality test. Both of these mathematicians, computer scientists, are still living, which is kind of a cool thing. We're getting into very recent territory in number theory. So this was the setup we were looking at last time. We have some integer n that we want to test whether or not n is prime. We've picked some a that is a residue mod n, and the first thing that we've done is we've calculated what is the greatest common divisor of a and n. That is a very simple thing to do. We just run it through Euclid's algorithm, and if we get a GCD of 1, then they're relatively prime, and we're going to go through the rest of this test. If we didn't get 1 as the greatest common divisor, then obviously n is composite. No test necessary. So we want n to be a prime number. One of the ways we can detect that is by checking that Fermat's little theorem actually works. And I do see, I see already a typo in here. These should be capital N's in my exponents. Sorry about that. That will be corrected on the slides I post to the website. So I want to check is a to the power n take 1 should give me 1 modulo n. That's something that is true for all prime numbers. If I don't get a to the power n take 1 is 1 modulo n, that tells me immediately that n has to be composite. That's exactly the basis of the test we were looking at last time. Yesterday for me. I don't know if that was yesterday for you. Now, we can definitively say when this test tells me I've got a composite number. But if I get what I'm expecting, if I get a to the power n take 1 is 1 modulo n, well, n could be a prime number. All prime numbers will satisfy this congruence. But some composite numbers also will satisfy this kind of a congruence. So the best that we can say, we don't have enough information after performing this test, we'll say that n is a base A pseudoprime. As far as the residue A is concerned, n is pretty much a prime number, as close as we can tell, but not definitively an actual prime. Again, so this was the test we were looking at last time. You should be ready to identify pseudoprimes on a quiz. So I can say, is the number 73 a pseudoprime to the base 10? You'll take 10 to the power 72, check whether or not you get 1 modulo 73. If yes, you get 1, it's a pseudoprime. If no, you don't get 1, it's composite. So that is something that I will be expecting in the near future. The problem we ran into yesterday is that there are some numbers that will always be pseudoprime no matter what residue A we picked. Now there's two names for this in common usage. You could say that these are the absolute pseudoprimes. They are pseudoprime for every single test you could possibly throw at them. Or another common name is to call these the Carmichael numbers. Same idea, we're just paying a little homage to the mathematician who conjectured that there would be infinitely many of these numbers. And that turns out to be true. There are, in fact, infinitely many Carmichael numbers. So 561 is the smallest. I've skipped a couple. 1729 is there on that list, and so on. So I want a different primality test that does not have the possibility of false positives in the same way. Let's take a look at how that primality test is supposed to be working. So this congruence should be true for every single prime number. It is true for every single prime number. I know that my Euler phi function of p is just p take 1. Any residue that is not 0 mod p gives me back 1 when I take a to the power p take 1. But let's refine this a little bit by examining what we get for the actual exponent p minus 1. I know that there's only one even prime number. Don't think about it too hard. All other even numbers, starting with 4, are composite. So if I'm in the business of testing whether or not a number is prime, and I pick some random number that's even, I can immediately throw it out. Remember, I'm looking for primes with like hundreds of digits or thousands of digits, so I'm never going to want the prime number 2 for this. And if I get something that ends in a 0 or a 2 or a 4 or a 6 or an 8, any of those numbers will be even, which means that they will be composite, and that's not what I want. So if I'm attempting a test for primality, I only am interested in odd numbers. Well, if p is an odd number, then this exponent that I'm looking at, p take 1, has to be even, right? 1 less than an odd number is an even number. So for the fact that I am taking something to a power, right? I'm taking my residue p, my residue a, raise it to the power p minus 1, and my test is to check whether or not I get 1 modulo p. But since p minus 1 is even, then this fraction, p minus 1 divided by 2, that's actually an integer. So I can rewrite the congruence and say, let's first take a to the power p minus 1 on 2, which we can do. This fraction is just an integer. I can quickly exponentiate and figure out a to that power. Once I have a to that power, it's only one more step to square it and see whether or not I get 1. So if I bundle up all this stuff that's in parentheses, I'm really asking, what are the solutions of x squared congruent to 1 mod p? Now, this is a super simple question in the integers, the rational numbers, the real numbers, even the complex numbers. There's only the 2 solutions, positive 1 and negative 1. And those 2 solutions will still work here. From the previous slide, I have subtracted 1 on both sides of the congruence. On the left-hand side, I've got x squared take 1. On the right-hand side, I've got this 0. And I can always factor my polynomial here, and I get x plus 1 times x minus 1. Hey, that's that same factorization by difference of squares that I mentioned a couple lectures ago. That's still working. So no matter what, if p is prime or if p is a composite number by accident, these two solutions will always work. X equals positive 1 will make this bit 0, the whole thing goes away. X equals minus 1 will make this bit 0, the whole thing will be 0. Great. But I need to be a little bit more careful than that before I can say those are the only two solutions. We've been seeing for a while now that multiplying modulo a composite number can have some weird stuff coming up. So let's look at some weird stuff. Let's take a modulus 12. It is even, so yeah, I wouldn't be testing this one to see whether or not it's prime. But it's a nice small number, and we've looked at the multiplicative units of 12 before. So I can write out all of the solutions to this congruence, and there's actually more than 2 of them. There's 4 solutions to this congruence. I can check, well, here's my 1. That's always a solution. Here's my -1. I just wrote it as 11 because 11 is congruent to -1 modulo 12. So those 2 will always be solutions. But I also pick up 2 more, 5 and 7. If you don't believe me, plug in x equals 5. Here I'll get 6. Here I'll get 4. 6 by 4 is 24, which brings me to 0, mod 12. So 5, which is not 1, and 5 is also not -1, but 5 is a solution of this equation. So I get extra solutions modulo composite numbers. That is a pretty weird thing. Like, if I have just completely turned your head upside down about everything you've learned in public school algebra, yeah, this is really weird stuff. Oh, getting carried away. There's another typo. I should never be looking mod 0. So, if p was prime, then I have this factorization congruent to 0, and this should be modulo p. I want to say that should mean that one of these 2 factors is 0, mod p. This is something I cannot say with the mod 12 case. I can write up this equation. I can have 2 different numbers, both of which are not 0, brings me to 0 mod 12. That's clearly demonstrated here. And that happens because 12 is composite. For a prime number, I say anytime I've got a congruence, stuff congruent to 0 means that p divides the stuff that I've got. So p has to be a divisor of the product x plus 1 times x minus 1. So I can use the fundamental theorem of arithmetic. I can use unique factorization into primes to say p divides a product. So p has to either divide this number, right? This is just some integer. It has a unique factorization. If there aren't any p's in the factorization of x plus 1, there had better be some p's in the factorization of x minus 1, because there are certainly primes p occurring in the factorization of this integer, and that's just listing out what's all the primes here times all the primes there. Does that make sense? This is something that's special about prime numbers. And the payoff is that the congruence I'm looking at only has the two solutions if I'm looking modulo a prime number, and it can potentially have more solutions if I'm looking modulo a composite number. So this is the algebra that's going to let me detect prime numbers. I'm looking for when does this equation have more than two solutions. So when have we horribly broken algebra? When do we find a quadratic with more than two solutions? Well, that means we're working mod a composite number. Those are the bad ones. We don't want them. So I've been talking about raising a to a power, getting back to 1 mod p. If a to the p take 1 divided by 2 power is a solution of x squared congruent to 1 mod p, and p is an odd prime, well then I've got this stuff in parentheses, squared gives me 1 mod p. So it must be the stuff in parentheses is either plus or minus 1 mod p. So if p is some random odd number that we're testing, and we find an a where p to this power is not plus or minus 1, but it does solve this congruence, a to the power p take 1 is congruent to 1, that means the residue a has given us information that p is actually composite. So think about this. Yesterday we were looking at the Carmichael numbers. We said that any residue a, relatively prime to the Carmichael number, to the power p minus 1 will always give me 1. We showed that for the number 561. It could be that a to the power p take 1 on 2, so that would be a to the 280. It could be that a to the 280 is something besides plus or minus 1. But that would mean that this number here is an extra square root of 1. There's only supposed to be 2 of those when you're working mod a prime. There's only supposed to be 2 square roots of 1 at all in normal algebra, but we're not working in normal algebra. So let's see this in action. Here is an odd composite number. Here is an a that I want to check. So I look at p take 1, which is 14. And this should be an exponent. So I calculate 4 to the power 14 mod 15, and I get 1. But 4 is not congruent to plus or minus 1 mod 15. I calculate my exponent, my p take 1 on 2, that's 7. I'll tell you that 4 to the power 7 is just 4 mod 15. So 4 squared is 16. I'll get 1. Yeah, that means that 4 is a square root of 1. But the only numbers I'm supposed to be having as the square root of 1 are 1 itself and 14, right? 15 minus 1. So because I have an extra square root of 1, that means that 15 has to be a prime number. All right, we already knew that that means that 15 has to be a composite number. We already knew that 15 was a composite number. It's just 3 times 5, but we're sticking with small numbers to see the algebra at work. So here's the idea for this test. we have some random odd number we want to check whether or not p is prime. Again, if it's an even number, we already know it's either the prime 2 or it's some composite number. So we're not worried about even numbers. Pick some a from 2 to p minus 1. We're going to check its GCD just in case. If we don't get GCD of a and p is 1, we just found out the p is composite because it has some non-trivial divisor. Otherwise, we're going to go on to the next step. If a to the power p take 1 divided by 2 is not plus or minus 1 modulo p, p has to be composite. It has to. Because if it was prime, I'm supposed to square this number and get 1. But also, if it's prime, the only numbers that square to give 1 are plus and minus 1. So if I can satisfy this congruence mod p, p is composite, for sure. Now, if I follow this formula and I do get 1 mod p, p might be prime as far as a is concerned, but there could also be some composite numbers that satisfy this congruence, kind of like we saw with the test from the previous lecture. So, does this identify 561 as a composite number, right? 561 is our smallest Carmichael number. I at least want to see if my new test idea fixes the problem I had with 561. And yeah, it does. So if I take a equals 5, I already know from last time 5 to the power 560 is 1 modulo 561, and I know that because 561 is a Carmichael number. We actually proved that any of these residues to the power 560 will give me 1 mod 561. But if I look to half of that exponent, if I calculate 5 to the power 280, I'll get 67. And 67 is not 1 mod 561, and 67 is also not minus 1 mod 561. So 67 is a square root of 1, but it's an extra square root of 1. We're not supposed to have that when we work with a prime number. So this test has told me that the Carmichael number 561 is composite, and it does this when my previous test failed to identify 561 as composite. I'm going to keep on with this example to refine this testing idea. So what would happen if I took 67 as my test? Well, I already know that 67 squared gives me 1. So 67 to the power 280 should also give me 1, and it does. Does 67 identify 561 as a composite number? So if I tried the test from last time, I get 1 mod 561, which says that 561 is a pseudoprime to the base 67. So I divide that exponent by 2, and 67 to the power 280 is still 1 mod 561. So it still looks like a prime. Maybe, though, I can continue to divide this exponent because this exponent is still even. I started down this rabbit hole of square roots because I noticed my exponents were even. Let's divide out another 2 and see what we get. So that would mean let's check 67 to the power 140. And yep, 67 to the power 140 is still 1 mod 561. Still looks like a prime. Let's keep going. 67 to the power 70 is still 1 mod 561, still an even exponent. So we're going to go one more time and try 67 to the power 35. And I'll tell you that 67 to the power 35 is congruent to 67 mod 561. And now this is a problem. 67 squared is 1 mod 561. Okay, yeah, I already said this business 2 slides ago when we were talking about 5. But notice that what I'm doing is I'm always dividing my exponents in half, because if I get 1, the square root of 1 should only be 1 or minus 1. As long as I have an even exponent, I can keep dividing out to do cheap square roots. And the problem is at the very bottom of the stack, I get a square root of 1, which was not plus or minus 1. So let's build this idea into our test. 67 by itself, for my earlier idea, would not have told me that 561 was composite, except for when I divide the exponents, when I divide all the 2's out of that exponent. So here is the actual 5th primality test that we're going to talk about. This one has a name. This is Miller's test. The steps should be pretty familiar at this point. We're going to let p be some odd number, pick some residue a between 2 and p minus 1, check the GCD just because we can, and that's cheap to do. If we do have some relatively prime residue, we're going to go on to the next step. Because p minus 1 is even, we're going to divide out by 2's, plural, on the 2's. S is not a number here. We're going to divide out by 2's until we get some odd number m, right? P minus 1 is even. Its unique factorization is 2 to the power k times some odd number m. And I want that m. If a to the power m is plus or minus 1, then p passes Miller's test. Because I know if I square this, I'll get a to the power 2m, and that's got to be 1. Keep squaring, eventually I'll get to a to the power 2 to the k m. That'll still be 1. And so if you pass Miller's test, p might be prime. I can't say for sure. But if a to the power m is not one of these numbers, if a to the power m is not plus or minus 1, we're going to go to the next step. So a to the power m is not plus or minus 1. We're going to square it. If that square, a to the power 2m, is congruent to 1 mod p, then p fails Miller's test. So what have we done? Right here, I have some number which is not plus or minus 1. Its square is 1. So p has extra square roots of 1, which means p is composite. You have failed the test. You are definitely not a prime number. If a to the power 2m is congruent to minus 1, then p passes Miller's test. P might be a prime number, because the next squaring I'll definitely get 1, and it's okay to have minus 1 as the square root of 1. That's allowed. So the only other thing that could happen now, right, these are my 2 exit conditions. Otherwise, I've found out that a to the power m is not plus or minus 1, and now I squared it, and I found that a to the power 2m is also not plus or minus 1. So maybe I could square this number and get a square root of 1, but I got to do that in the next step of my calculation. So if I get this far in the algorithm, I got to do another step. So we're going to keep on squaring. And when we square, we'll get some number that looks like this. A to the power 2 to the power s, and then times m. We're going to keep on squaring until we get this number looking like -1. Or if we go all the way up to the kth squaring. So k here was my number from this slide. That's the k is the number of 2's in the factorization of p minus 1. So these are two different exit conditions. So if I ever get one of these numbers, a to the power 2s times m is -1 modulo p, then p passed the test, p might be a prime. And likewise, if I get all the way up to the kth power, then again, p passed the test, p might be prime. That's really a way to bundle in yesterday's test, because if s equals k, I'm just looking at a to the power p minus 1. If instead we get something like this, a to the power 2 to the power s times m is not plus or minus 1, and a to the power 2 to the power s plus 1 times m. So this number down here is the square of this number up here. So if I square something that is not plus or minus 1, and I get 1 out of that squaring, then p fails Miller's test, and p is definitely composite. So you can start to see a pattern here. I start at the very bottom of the chain. I've got my a to the power m, and what I'm looking out for is, does repeatedly squaring this number ever give me a square root of 1 besides 1 and minus 1? If you definitely get that, you have failed the test, and you've definitely got a composite number on your hands. There's some exit conditions here to save yourself some effort. Obviously, if you keep squaring and you eventually land on a -1, then you're not going to find one of these illegal square roots of 1. You'll just have -1 is the square root of 1. Okay, cool, great. So in that case, if you pass the test, then p is maybe a prime number, maybe composite. Again, this is a fairly simple calculation to do. We just take p minus 1, divide out all the 2's, and do some repeated squaring in modular arithmetic. So we've been doing these kinds of things in class for a while. We just have a slightly different goal this time around. So please do be prepared to perform this on your own, using a calculator for the factorization in the modular arithmetic. Now here is a fact. I'm not going to prove this. You can just have it for free. Every composite p that we would want to be trying for this test, so some odd integer greater than 2, fails Miller's test for at least 3/4 of the bases a that we'd be looking at. Oh, and this should be a p. So even though some composite numbers will beat Miller's test some of the time, none of those numbers will beat Miller's test all of the time. So there are no absolute pseudo-primes for the Miller test. There's no version of Carmichael numbers here. Now this 3/4 idea can put us in the direction of looking at probability. I said before, if you pass the test, I don't know for sure whether or not I've got a prime number on my hands. So this fact here is telling me if I've got some number p and I pick some base A and I pass Miller's test, well, it could be that I just didn't pick the right A. So there's a 1 in 4 chance that I picked the wrong A and it looks like P is prime, but it's actually composite. But that also means there's a 3/4 chance I picked a good A and it really is the case that P is prime. So if I go through Miller's test and I pass Miller's test, I have a 3/4 chance, or a 75% chance, that my number P is actually prime like I wanted. So let's work this in. Let's get some probability working for us. Now this is Rabin's probabilistic test, or sometimes people will call this the Miller-Rabin test. Setup's pretty much the same. Let P be an odd integer. We're going to pick k different bases, A1, A2, AK, the whole list, at random between 2 and P minus 1. So this is a test that we can make easier or harder depending on how much time we have for computation. We're going to use these different bases to run Miller's test k different times. If P fails for any of those tests, even a single one, that means that P is definitely composite, and we have failed the test. If P passes each different run of Miller's test, well, P might be prime, P might be composite. But we can actually give our confidence on the matter. P is prime about this often. So our probability will be 1 minus 1/4 to the power k. So the chance that you have some composite number beat the test would have been 1/4 to the power k, because it beat k different tests, which were all independent. So the probability that we actually have a prime number is going to be 1 minus that. So for example, if we have some 1,000-digit number P that passes 10 different rounds of Miller's test, so we said, okay, let's do the Rabin probabilistic test. We're going to run Miller's 10 different times. We passed it every single time. Then the probability that this number is prime is 1 minus 1/4 to the power 10. And if you prefer decimals, throw a percent sign on that. That's going to be 99.99990463%. So better than 1% of 1% of 1%. And, it's not definitive. I don't definitely know that this number P passes the test, but good enough for government work, I'd say. Yeah, 1% of 1% of 1%. Pretty good margin of error. So in practice, let's say that I don't need so small a margin of error. How many rounds do I need to use to get my confidence that I want? It all depends on how much I'm willing to do, how much work I'm willing to put in to be X% sure. So for example, if I want to be 80% sure I've got a prime number, I'm going to set up this formula that says my confidence is 80%. That should be 1 minus 1/4 to the power k. K is the number of rounds I have done in the test. And I'm just going to solve for k. I move some stuff around. It says 1/4 to the power k is 0.2. If I want to solve for k, I'm going to be using logarithms. So my base is 1/4. K should be the log base 1/4 of 0.2. That's how I can extract the k out of this equation. And if you want to calculate log base 1/4, take any logarithm you want. Calculate log of 0.2, divide that by log of a quarter. So this could be common log, this could be natural log, this could be log base 3. Any of them, this formula will work. So this is just the generic conversion formula for logarithms. And I get a little over 1. Remember, if I did one round of Miller's test, I've got 75% confidence, so this formula is telling me I don't even need a whole second test to get the confidence that I want. But since I can't do fractional tests, I gotta run at least 2 tests. 2 successes, and I'll be guaranteed at least 80% chance that I've got a prime number on my hands. Right. What's the actual percentage? I'd say I've got 1 take 0.25 squared. So that's actually 93% and, 3/4 of another percent. So even better than my 80% that I wanted. And this is a test we can use. So if I wanted 93% chance of actually having a prime number on my hands, even if it's some 10,000 digit long number, I'll just say, well, my k has got to be 2. So I pick 2 different bases, a1 and a2, and they can just be any random number between 2 and p. I'm going to run Miller's test twice, and if I fail either of those tests, I know that my number is composite, and I'll have to pick some other number I want to test. If I pass 2 rounds of Miller's test, then I know I've got a 93% chance that the number I'm looking at is prime. That's a lot of information for not very much work. Now, in order to make this practical, there's one additional piece that we're going to need. So I mentioned towards the beginning of term that prime numbers spread out the farther you go on the number line, and that's true. It's harder to find large prime numbers than for small prime numbers, just because they bunch up closer towards small integers. When you're a small integer, there's only so many prime factors you could have. When you're a big integer, there's lots and lots of factors you could have. So it's harder for large numbers to be prime. In order to make a probabilistic test like this, where I'm picking some random integer, I'm doing some tests to quickly get an idea, okay, I want to be like 95% sure that this number's prime. It could be that the numbers I'm looking at are so huge that if I'm just bouncing around randomly, maybe it's unlikely that I get a prime number. So in order to put this into practice, I need to have an idea of what the density of prime numbers are. So as I go out farther on the number line, how frequently should I find a prime number if I'm just picking them at random? And I've got some good news. I'll fill in the details with next week's lecture. The good news is this actually works. And the reason it works goes back to some really important theorems in analytic number theory, which is the application of calculus to number theory. It's a bit more advanced than we're going to be dealing with in this class, so I'm going to quote the relevant theorem and talk about how we can use these density estimates to get our job done and say for certain how much work do I need to put in to find some random prime number with at least 1,000 digits. That's the question that I want to answer in order to set up an effective encryption system using RSA. Whew. Okay. So it's been an interesting week. As I mentioned online, our test will be postponed. So this was originally scheduled for Friday, 3 April. That will now be taking place after our break. I don't know when the test will be scheduled, because I'm still trying to work out how to work online assessment into the test. So next week we will continue to have these recorded lectures. I'm starting to feel like I'm getting a little better at them. Again, if you have any feedback for these things, please let me know, and I will try to up my game and make these better for you. Thanks for being here. See ya.